Yeah, so today I'm going to talk a little bit about codification in the medical domain. And what is the existing role of LLMs and how we can use it responsibly to assist healthcare data research. So I'm looking at a case study of OMOP mapping, and my talk will be explaining to you what OMOP mapping, if you've never heard about it before, natural language processing solution, the computer science aspects of the framework. And then we're going to talk about the responsible research and innovation aspects of the research as well, because as we're dealing with healthcare data and healthcare and potential impacts in lives and livelihoods, how we can use AI responsibly in our practices to use responsible research and innovation in our research and our findings so far. So when we're dealing with OMOP, OMOP stands for Observational Medical Outcomes. So it's pretty much codification of certain conditions or drugs or observations within the medical domain. So for every diagnostics or clinical information about patients, there is a codification that is standardized so that data that's collected from different hospitals, different countries, different locations, different doctors, it can be made eventually interoperable. And when we're talking about healthcare data, especially within the UK, that there's so much richness of electronic health records and GP data being collected, what we want to be able to do is to somehow make this data interoperable so we can create more power and have more robust predictive models. And when we're talking about power, we're talking about quantity and quality of data as well. So we need to have like all sorts of silos where this data is collected and is protected to protect privacy of patients and individuals. It needs to be somewhat findable. So if we want to do research in breast cancer, for example, we want to understand which research groups are collecting data, which GP practices or which hospitals have breast cancer data, what are the characteristics of the individuals, and can we use this data to support our research, our clinical trials, or like advanced medical research. So when we're talking about OMOP, is a codification that allows for the translation of raw medical data into code that allows it to be interoperable in the future. So, for example, if you go to your GP and your GP diagnoses you with high blood pressure, for example, in his notes, he could put high BP, he could put elevated blood pressure, high blood pressure. It means the same thing, but the words are different. So how we can make them codified to the same concept within the same context. So when we are doing research of individuals with high blood pressure, we are retrieving the correct data set and we're finding the correct data set. Does that make sense? So this is the problem at hand. So the OMOP mapping steps is quite complicated because first in the medical domain, there's a lot of uncertainty around diagnostics. And diagnostics is also based on context. So currently, the mapping process, getting the raw data and turning it into codification requires a team of data engineers, clinicians, allied researchers, and people who have expertise in a particular domain. They will understand what are the objectives of the mapping. Is it for clinical trials? Is it for research? Is it for clinical research? They need to understand the data and the context. They need to define the vocabulary, so which codification we're going to get our raw data and transform it into, use existing tools for mapping, validate, and then eventually release it for checks and for research in the future. So these are the main steps. This is extremely laborious, this is extremely resource intensive, and it's passive to a lot of errors. So just to give you one example, we worked lately with self-reported medication. So we got questionnaires from patients, and they were reporting the medications that they were taking. And you will soon realize that when people are typing questionnaires, there will be typos, there will be errors, there will be a lot of uncertainty on how the data is inputted into the system. But that doesn't mean that the data is not useful. We just need to understand how to make sense of it. So one existing tool to be able to help us with identifying codification for this medication, Nasonex, for each nostril, is a website called Athena. Athena is the Bible of OMOP. It's where you find all existing vocabularies and codifications. But if you search this in the Athena website, you're going to find 123,000 codifications. So that's how difficult it is. And the humans need to educate which one is the most suitable for the context. So it's a very complicated problem. If you use existing tools that are out there that can help you, some use lexical search. So they will try to find words that are similar enough and then suggest the codification for it. But in this case, and obviously we picked a very tricky case because there was the parenthesis that the individual input into the system. You have loads of suggestions that have absolutely nothing to do with the medication and one that is a hit. So it somewhat helps the data engineers to narrow down the search, but still not ideal. And that's where there is the motivation for us to try using large language models or more intelligent natural language processing models. So that was the motivation for our work, is dealing with this healthcare problem that is dealing with medical data. The medical data will be messy, will be uncertain, and the problem is very hard. So talking to data engineers, all of them agree, well, many of the data engineers that we've worked with, they agree that there is the need for better tools. And they agree that there's room for AI to support with those challenges. So what we've created as our solution is a pipeline that involves natural language processing, including large language models. We wanted it to be open source because we wanted to be made available for the community to scrutinize our solution, but also to be able to use it widely because we want to support healthcare research. It's privacy preserving, and the way we've engineered the solution is it allowed for you to work on your desktop. So if you're a data engineer in a hospital in Nottingham, your data cannot move, you can install it in your own desktop and use it to help with mapping, but it can be installed within trusted research environments and use that, or it can be used in the cloud. So we modularized it quite a lot in our engineer to make sure that it addresses most needs. But again, being open source, we always invite the community to be able to contribute to a possible solution. So if you want to know a little bit more about the paper and the implementation, our solution, we call it Lettuce. And because we work in a group that's creating solutions that have to do with rabbits. So there is one solution called Carrot, there's one solution called Hutch. And then our large language model had to start with L, and then we said, oh, let's go for letters. So what we have is, in terms of the overall architecture, and I'll try not to be very techy here on the computer science, but if you have any further questions, I'm happy to answer afterwards, is we'll have an input that will give us the source terms. So it will give us the queries, the Nasonex, the aspirin, or other concepts. We will codify it in a vectorized manner. So we try to get the concepts that are semantically similar, and we codify them in a way that they will be close to each other. And then the first thing that we will do is a vector search. So we will do a semantic search within the data set. If we are able to find the solution within the semantic search for the adequate concept, we go to the OMOP data set and we get the code straight away. If not, we give the top 10 searches from the semantic search and we give it to the LLM. The LLM will use RAG, which is retrieve augmented generation. So they use the OMOP data in their rationale, and it will educate which ones are the best suggestions. And if no suggestion that was given by the vector search, it can suggest something else. So we have 3 steps by which we try to identify the codification. And then we provide the mapping recommendation. So we don't provide a single solution, we provide a list of the top K most suitable codifications, and we let the data engineer decide. To try and optimize this pipeline, instead of deciding on which large language model we were going to use, are we going to use ChatGPT, are you going to use Gemini or Llama? We've created a framework that agnostic, both in terms of embedding the data, codifying the data in a way that semantic concepts are close together, but also the LLM model that will be chosen. So we have like a tool called Lattice Inspector, where we can combine different data representations, because we realize that how you represent the data and data within context impacts the outcome. So it's not just about you going to OpenAI and doing a course on RAG that you're going to get the best LLM results. You need to do a lot of research on how your data will be represented. We've tried different types of embedding models, which different models that codify the data, and we've tried several LLMs. And the reason why we've done that is because we will have solutions that are to be run within different hospitals and different NHS organizations. Some of them will have a lot of money and they can have the biggest model ever. Some of them will have less budget, so we need to be able to find smaller models that consume less resources, but still they can be run within Lattice. And then we tested all of them to try and understand what's the minimum that we can get in terms of resources usage that still allows us to get a good result. So the results that we've got using the benchmark is that Lattice helps a lot, considerably, and it matches human annotations 65% of the cases. And it looks like it's not a lot, but if you talk to a data engineer and he has like 2,000 patients that they need to map it, it will take him 2 months. So if we cut the workload by a month and a half, plus giving suggestions that the data engineer can help us improve the tool, it accelerates the whole process massively. using RAG, so using the LLMs within context, improved all the models that we've used. And even with the smallest model, we've achieved 57% of accuracy. And then the question that came to my mind, which is probably the most exciting and important research question of this talk is, can we now get lettuce and deploy it widely? What do you guys think? No? Why? Data governance. What else? Control. Validation. Can we fire all the humans? No, I don't think we can. Yeah. So knowing that we were able to design a tool that does accelerate, that does help a lot humans, how we can make it better and how we can deploy it responsibly. So this is what we've done next, which is an ongoing research, by the way. So this is a spoiler. There's still no paper about it, but hopefully to be soon. We partner up with colleagues from Nottingham that investigate the use of responsible research and innovation. And responsible research and innovation is an area that try to understand and anticipate and mitigate negative impacts of you launching a product, and in our case, launching an AI product. And there are loads of things that we need to consider. So is a lettuce useful for codified data for all ethnicities, for rare diseases? Is it fair? Is it unbiased? If it's biased, do we know what are the possible biases and the risks of using this tool more widely? What is the data governance around different silos that use or will potentially use lettuce for OMOP mapping? What is the ethics of using lettuce? Are we taking out jobs, or are we accelerating the productivity of individuals, a lot, freeing them time to do like more complicated work instead? How can we trust the outcomes from lettuce? So what we've decided to do is to adopt a methodology that was introduced within the EPSRC website framework, and it's the area 4P framework, which is you trying to anticipate what are the possible issues that you're going to have when deploying your technology, reflect about it, engage with stakeholders, and have like in-depth conversations, and act on what are the possible risks that you're going to have with this technology. And then they've extended it and created 4Ps, where you try to understand when you're creating your technology, what's the purpose of this technology? Who are the people who are going to be involved and impacted? What are the processes around this technology? And what is the impact of the product? So the University of Nottingham and colleagues, they've created methodology using prompts and card suits. So what we've done is run workshops with a bunch of stakeholders in the OMOP community, a lot of data engineers and people who use OMOP on a daily basis. And we started asking them questions around risks. What are within the processes of OMOP mapping and the steps, what they anticipated as risks, and what were the challenges of mapping as a human, and what would be the challenges for machines to map it. And then the objective of the workshop was identify technical and ethical risks of deploying these tools, produce a risk register, understand common pitfalls when integrating AI and OMOP, incorporate the Area 4P framework in our discussion, and how we can create solutions together and mitigate these problems. So the first workshop that we ran was 2 weeks ago. So we had like a 4-hour workshop discussing many challenges around the technology and trying to understand what was the challenge for humans to do the mapping and what we would have to bear in mind when implementing the LLMs and deploying them. So things that came up that were technical and challenges concerns is like the interoperability of local mapping. So if we deploy Lettuce version 1 in Nottingham using one LLM and another Lettuce in Swansea using LLM 2, with different data engineers operating these tools? What is the interoperability and the differences and the local biases that might have with those models? And if we are not allowed to combine this data because of governance, how we make sure that we fine-tune a model and then that will be reflected to other models as well. So this is an open question, but this is something that came up. Transparency, when the LLMs are making a decision, we want to know why you're making the decision. How did you came up with this conclusion? What are the stats behind it? What is the rationale about it, around it? Biases, are there any biases? Are you codifying things just for male, white, of a certain age, or are we codifying things that take into consideration a more diverse population or rare diseases or rare cases as well? So we need to understand that. Provenance, which is the justification of the mapping, proper assessment and validation, privacy. We need to make sure that these machines are going there, looking at personal healthcare data and keeping the privacy of the patients. We need to prevent replication of human errors. Yeah, and if we're training machines with data that has human errors, these will be replicated and model fine-tuning. And in terms of the responsible research and innovation concerns, more that have to do with the humans involved in the research, again, is privacy, confirmation bias, disclosure, sustainability. There were loads of concerns about how much energy these models will take to run, accountability. So once you deploy these models, who is going to be accountable when the mapping is wrong? And then the dilemma between what's rare and disclosure. Because if you have like one hospital where you have 5 patients with a particular disease, there is disclosure there. So, but you need to be able to map them because you want the LLMs to understand that that's a rare disease and how to map it. There was a massive concern on over-reliance of this technology. So data engineers just letting the LLMs and these AI solutions to do the job without them checking. I think there was a paper from Harvard this week saying that people are getting dumber because they're using too much ChatGPTs, and it is the over-reliance, and that tends to happen. So how we can keep checks to make sure that the knowledge doesn't get lost, knowledge of these data engineers that have years of experience doesn't get lost. And the role of humans in credit assignment as well. So this data is being trained on expertise of many, many years of individuals. So how do they get credit? So the initial recommendations that came out of it is, yes, AI is needed. It's a laborious work. We need support, but we need to have the human in the loop at all stages, providing data to the models, helping validation, helping deciding the final mapping solution, helping defining what's the provenance and the final checks. Transparency, recording the provenance and the decisions, and research is needed to understand how AI can provide a justification for the mappings. So the next thing we're going to do is to sit with data engineers and say, if AI was going to tell you, this is the mapping that we came up with. What is the steps that you need to know to be able to double check that what the rationale provided makes sense? And there's the need for joint effort. So in the future, what we want to be able to do is have a Lattice plus plus, where we add all these different characteristics of responsible research and innovation. And we create a human collaborative tool that is a little bit more responsible. But the idea is once we incorporate some of these responsible elements, we continue having workshops to try to anticipate what might come up next. That might be a responsibility challenge. So in conclusions, just to finalize the talk, it's an open source tool that accelerates OMOP mapping, Lattice, the tool that we've created. It has a need, and the importance has been acknowledgement, but it needs to be a human cooperation tool. Data representation is key because we saw starking differences in outcomes if you don't embed the data properly and you don't add context properly. Needs to be used responsibly, and we need to avoid over-reliance. And we need, for any LLM solution, you need to have the early engagement of the stakeholders to be able to understand risks. So the message here is when you are developing these AI tools, responsible research and innovation is an ongoing process that you incorporate into your products, but you need to ever so often revisit it to see if there's anything else that needs improvement for safety of individuals, patients, and vulnerable populations, and everybody in general. Thank you. That's it for me. So this is the team working in Lattice.
So, could I ask if there are any questions for Graciela?
Hello, thank you for the presentation. How many classifications can you do a second in Lattice?
The microphone.
But we tested, I think, 400 inputs, and it's like a matter of seconds. Yeah, it's very quick. Just need to have the process that took longer for us is embedding the OMOP data set into that pipeline, because the OMOP data set is 6 gigabytes. So it takes 2 hours to embed that. After that, the decision is milliseconds.
Thanks a lot for the presentation. I was just wondering, how do you go about effectively anonymizing the patient data when you're dealing with free text fields? Is that something that you're able to actively solve during the development, or do you just accept that as a risk?
So generally, when the data comes to our team, the data is already anonymized. So we have ways of extracting, we deploy tools in the silos, and these tools stay there. And then we anonymize the data, and all the codification would be federated as well. So we wouldn't have any visibility of the data. And especially in research, in trusted research environments, they are very strict of the data that can come in and come out of the system. So some of the research that we're doing now is Fed Lattice, is trying to see if we can implement Lattice in a federated manner, and what can come out of these silos, the trusted research environments. We still don't know. But there's loads of reports. If you send me an email, I can send to you a report of trusted research environments and their concerns around the use of AI for disclosure control of healthcare data. Yeah, but they're very strict, and we'll have to abide by their governance.
Okay, so let's thank Graziella again for her talk.
Thank you. Hello, my name is Xin Yiwang, and I'm pleasure to be there and give the presentation. My topic is applying large language model to domain-specific task. I will use report generation for cases and show you how to apply it to this domain. Here is a related material. It's a survey of deep learning-based radiology report generation using multimodal inputs. It will contain lots of details about today's presentation, especially the technical detail. Here is the outline of my presentation. First, I will give you some background knowledge of radiology report generation and tell you two forms of applying large language models to specific tasks, and give you some details about the process. First, what is a radiology report? It's summarizing the image findings for clinical decisions. I give you an example here, and it has lots of sections. For the automatic generation, it's mostly for findings session and the expression sessions. But manually report generation is label intensive and time consuming and need a lot of domain specific knowledge. So now mostly it will exceed the medical system capacities. The situation even get worse. It will extend the patient's waiting time and increase the risk. So we're thinking of automatic this process. Well, the report generation is a multimodality problem. The physicians need to get information from from the clinical information of patients, like its age or its gender, and it also need to combine with the medical knowledge they learned and with the images to get the final reports. So how to apply LLM to it? First is we can deploy it directly, like I ask ChatGPT what is 100 add 100. But for medical field, for the report generation field, it has two problems. First, it's relatively less specialized expertise. It links the knowledge in the medical domain. And next, for now, the ChatGPT 4.0 is a multimodality models which can take image as input, but for the previous LLM, it only takes the language as the input. So we need to fine-tune the models for the specific domain. And when we want to apply, as I mentioned before, when we want to apply the large language model into this field, it meets two problems. The first is the previous LLMs cannot analyze the images, so we need to change it to a multimodal models. And the next is it do not have this domain knowledge, so we need to do a domain-specific fine-tuning. For the first problem, I will first show you a general workflow for deep learning-based methods, and then show how the large language model-based methods align with it. First, we will get multimodality inputs, such as images, clinical information, and then we will prepare this data, like do the image resizing and remove some noising from it, and also do this process for the text information. And next, we will do feature learnings, use different kinds of encoder to learn from image from text, and then we fuse or concatenate or make this information can interact with each other. Finally, we get features the input into the decoder to generate the final reports. So what the large language model can do, normally we take a prompt as an input and input into the large language model and get the output. So in the following steps, the large language models can do the step 3 and step 4. First, it can be a text encoder. It encodes the prompt, and then it can be a decoder to change the features into a report. Therefore, how to insert these images? Mostly, there will be a visual encoder to do the third step to encode the images to image features, and then there will be different adapters designed to align the visual features with the output text features to do this alignment. The next question is about the insufficient domain knowledge. So we how to make the general large language models know some medical knowledge. Firstly, I show you an example about Lava and LavaMade. LavaMade is a fine-tuned Lava-style models on medical data, and Lava is a general multimodal models add the visual encoder and the adapter to Llama models. And here is an example of the Lava-made output and lavas. If we input and check X-ray images and ask what is shown in these images, the Lava-made can tell you something about the medical some medical things, but the lava only can know that it is likely a medical illustration of diagram. It learn nothing about these images. So we want to what happened between the lava and lava-made? How to change lava to lava-made? Firstly, we need to get a large-scale domain-specific data to train these models, and then we need to design the prompt to make the model know what we want to get from it, and then we need to fine-tuning the model. First is about the large-scale domain-specific data, how to obtain it. There are two mainstream ways to get it. The first is release the large data set. In the medical field, for example, there is a public data set named PMC 50 million. There has 50 million image text pairs extracted from some medical research database. And next is data integration, like the Chickstreet. This is a large models that integrates from over 20 public data sets. They concatenate lots of public data set together to build a large data set enough to training a large language model. Next is the prompt design. Now in the report generation field, the prompt design is quite fixed. For different kinds of medical tasks, they will give fixed descriptions to let the models get the prompt. For disease classification, they will give an image. The model is required to diagnose if some disease existed. For other models, maybe they will give them a library. There are lots of fixed sentences, and when they training it, they randomly select one of the sentences in the library to input into the model. And next is about the fine-tuning technique. We already know that for large language models, there are very large parameter size demands. They need lots of GPU resources. So how to make it easier for us to use less GPU to train these models? The mainstream method is first is mixed precision training, and next is the quantization. These two are really mainstream. Everyone use them now, but they will maybe get a little bit accuracy decrease, but they will save lots of GPU resources. And next is a method named LoRa, low rank adaptation. This method is mainly proposed to solve the problem I will show you in the next slides, but it also can save a little bit GPU resources when training it. Then it's adapter. Adapter means some people use adapter with fully fine-tuning all model parameters, but some works will frozen the model's parameters and only train the adapters, so therefore they can save lots of GPU resources. And I will tell you about the LoRa. It's really popular method. It's the advantage of it is it can save the storage of the fine-tuning models. You know that if we have models with over 100 billion parameters, we save it. It needs a lot of storage, right? When we train a model, we need to store a model. But if we use it with LoRa, you can say for the fully fine tuning, it is 100 and over 100 billion parameters. And if we use LoRa, we only need to save about 4.7 million parameters. So the stored models is very small. So what is the large model performance? This is in the report generation domain, and it built a leaderboard for it. The models in the boxes is some traditional models other than the large models. The other models are the method trained based on large models. And you can see now the large models beat the traditional models, but not a lot. But one of its advantages is its better generalization abilities. These models are trained. You can see this is a test on the mimic dataset, and this model is trained on mimic dataset, and this is test on IUX ring is trained on also trained on mimic dataset. Although in the X-ray dataset, this model outperform others, but for other public dataset, like the checks plus or the read grade, the traditional model cannot beat the large multimodality models. Even these large models do not train on the specific data set. They also can give a good performance on this data set. I think not very good, but it's acceptable. So I think one of the advantages of large model is it has a better generalization ability. But we also need to, although it has advantages, but we also need to be aware of the prompt sensitivity of large models. Firstly, different prompts may yield different outputs for the same questions. I give you an example. It tests on the ChatGPT, and I ask it a medical problem. Does these sentences indicate the presence of a disease? If possible, indicate answer 1. If negative, it answer 0, and it give me 1. But I just do a very slight changes of the prompt. I just remove the possibility and let him, if indicate, answer 1. If negative, answer 0. It will give me 0. So sometimes it's not very sure about its answers. So we cannot rely on it. Only can use as a tool. I think you especially for the medical field. And and the other problem is it also tendency to accommodate users. It's also the same questions from before. And when it give me 1, and I think I give him, I don't think so. And then it's thinking a little bit, and and gave me that this hey, it also thinks the statement does not directly indicate the lung did not indicate the diseases. So it denied its previous output and I want to tell me I'm right. Yes. So really need to be aware of it. Next is the conclusion and future works. So we can say large language model show excellent generalization abilities for it, but for the medical field, it need more flexible prompt design because now we only use the fixed prompt to do it or some fixed library. And next, we need to, more robust models can overcome the prompt sensitivity problem. And we want to think about more about the large language models language scales. Now we mostly want to use use the large multimodality models. It seems not very good at the image analysis. That's all. Thank you for listening.
Thank you, Shini. And any questions from the audience? Any from the live chat? Okay. So I wonder where the human fit into this. Where does the human fit into this? So is it like assistant for the human looking at the report, or could it?
The system finally want to take an image as input and then can output accuracy report generation, and it can help the physicians to get the final reports. Yes, do not let the human into the loop. Yes, thank you.
So just on that note, do you have any thoughts about the issue of physicians overly relying on report generation by AI? Yeah, in the sense of, not making sure that they properly check it when you know that there's an accuracy limitation to the model.
They will. Okay, thank you. Maybe they will use it as a tool and they get a preliminary version, and then the physicians will modify them. Yeah, some hospital maybe do that. And now I think the physicians cannot totally believe the things AI output. Yes.
Okay, so we move on to the final talk by Anha. And we thank Shini again.
Can you reduce the sound on it?
You want to do it?
Yes.
Okay.
All right. Good afternoon, everyone. I'm Angs. I'm from Liverpool, and actually we computer science department. So today I could talk about physical intelligence, which is something that I think we believe that could be the future of intelligence. Yeah. So you may heard a lot about AI, right? So AI is artificial intelligence, and I think AI now in both industry and academic is a big topic, and actually it's turned out to become a billion, let's say, industry market. Yeah. So the interest of our research group is to to apply AI to the real robot, and by applying AI to the real robot, we call it something called physical intelligence, which is let's say we have something smart like the AI model like ChatGPT right now, and we have something that can walk around, interact with the environment, which is the robot. Yeah, you may not see too many robots that's walking around smartly in a nice way at the moment, but we may see that in a lot of applications. For example, let's say in autonomous driving, and we do have autonomous car running around, let's say our road at the moment right now. Yeah, so before we go to the technical detail of our talk, then I would like to introduce some of the research topic that we are doing. So we're interested in mostly the intersection between computer vision, machine learning, and robotics. And most of the time, we use text or images as the input for our problem. And then we try to solve different tasks, let's say, at the intersection of these three domains. For example, we do robotic grasping, we do foundation model and generative model for different tasks. Yeah, if you not familiar with generative model, then we would have some very big model. For example, let's take to video like OpenAI Sora or Google VO3 just released recently, and we try to do something similar, but of course a slightly different problem and much smaller scale. We also try to do efficient AI. So efficient AI means most of the big model recently, for example, like ChatGPT or Llama, Llama 1, Llama 2, Llama 3, any other big model, they are very costly to train and also very, let's say, expensive to deploy as well. So actually, a big model like ChatGPT, OpenAI need to spend, let's say, a lot of money to build the infrastructure just for inference, not only for the training. So a big question in machine learning and also in our research lab is how to make these models smaller, faster, and especially how to, let's say, make something that we can deploy to the edge device. For example, let's say a robot or our phone. So it's a very important task when we need to create a small model, because in many cases you don't have the internet, or for example, let's say you ride a car to somewhere that don't have the internet, and technically you cannot, let's say, send a request to the cloud and process the request. Yeah, so we also work in some topic in medical robot and medical imaging, and also freight learning as well. So these three topics is more or less connected together, because I think we have the first talk about medical report, and actually it's a big problem in medical field is the privacy of the data. So we need to train the data in a freighted learning manner, or simply it's a fully distributed learning mechanism. So freighted learning is, let's say, a distributed system where you can train the model without collecting the data. Yeah, and the application of freighted learning is a lot. And if you, let's say, if we hear about cryptography or Bitcoin, and actually it's a kind of, a field where pushing freighted learning a lot as well, apart from medical imaging and also medical report or different, let's say, application on, let's say, that require distributed or a privacy preserving application. Yep. So these are the field robot that we build in our lab. We build endovascular robot, which you can see on this side. I hope that you see in my mouse here. So literally it's a medical device, and we try to address the endovascular intervention, let's say, support the surgeon during the endovascular intervention. Yeah. We build both the real robot, we build the hardware as well, and then we build the simulator. The role of the simulator is if you don't have a robot, then you simply can use our simulator to deploy or to train your AI model. So literally, you don't need the real robot to let's say to develop your AI model. Yeah, the reason that we develop the simulator is because it's quite take time to develop the robot, and also if you want to test the robot, and we need to bring that to the medical room and actually use the X-ray machine. It's quite let's say costly to do, and also it's complex as well. During COVID, and we also deploy and develop a robot. It's just a simple mobile robot that can run around inside the hospital, and actually we deploy that to some hospital as well, because if you still remember, then one of the big problem during COVID is the contact between people, right? And we want to have a robot that can deliver food or medicine and support the, let's say, the surgeon and the nurse during the hospital during that time. Yeah. And in freighted learning, then we mostly work more on the theory side. we develop different methods that can reduce the training time. For example, if you have, let's say, 10 silo or 100 silo, X silo is one hospital or one autonomous car, then how these silo communicate and let's say jointly together train a model is a big question, because you simply don't want to wait a lot of time to let's say communicate or send the model around these silo. And then we also address some problem of the data, for example, like the linearity problem, when your data is very different from the data from other silo or from other hospital. Yeah, I think this is the vision part. I think we can go back to this part a little bit later. Apart from this one, then we do quite a lot of interesting work on generative AI. For example, in this video, then you can see there's a human motion, right? And one of the key things when we train any big model is you need the data, okay? And in this start, then we care about how to, let's say, generate human dancing motion from the music input. Yeah. And the first question is where the data that we can have. For example, let's say, if you want to get the dancing model like this, then you need the data, right? Yeah. So the data is simply we download it from YouTube, and then we try to have a method that can label a lot of data from YouTube, and then transfer the data from YouTube from 2D to 3D. So literally the video that you see here is the 2D video from YouTube that you can see, let's say, every day. And the reconstructed model here is the 3D motion of the same video, but it in 3D. Yeah. So the application can be various. For example, let's say when you make when you want to make an animation movie, or when you want to let's say make some let's say high profile, high views video for example like TikTok, etc. Yeah, so I think in this work, then we mostly just create a data set, and that the data set actually serves the foundation for developing our the model later on. Yeah, the video have the sound as well, but I just mute the sound for the slide. Yeah, so when we talk about, let's say, group dance, then there's a concept about the consistency and the diversity. So consistency means several dancers in a group will dance more or less very similar, and diversities mean the dancer in the group will dance of course very different, but still need to follow the let's say the music beat and rhythm, of course. Yeah, so we also have an AI model developing like this, so this problem, and then the main contribution here is we want to have the model that can control the consistency and the diversity of your dance group. So it's just like if you want to dance very differently from your group, then let's say you can control that, or if you want to have the group dancing motion which are very similar to each other, then you can control that parameter to generate the let's say the desired outcome. Yeah. So let's go to the main part of the talk. So today I would like to talk about physical intelligence. So yeah. So let's bring up some robotic tasks. Oops. I think this video cannot be flat. It's fine. Yeah. So when we talk about robotic tasks, and actually we usually can classify all the robotic tasks into two big domains. One is manipulation and one is locomotion or navigation. So for example, if you have a humanoid or a quadruped robot, and it's a locomotion task. If you have an autonomous car, then it's a navigation task. It's like running around, walking around. And the manipulation task is actually less complicated. So manipulation task means, for example, here you have a robot arm here, and then you want to open the microwave. So it's a very kind of common task in robotic research. Yeah, the application of robotic manipulation can be various. For example, let's say if you have a chance to visit Amazon warehouse, and you see that they have thousands of robots that can do different, let's say, pick and place task, and actually the package that we receive from Amazon more or less will have the robot, let's say, contribution from there. Yeah, so the question that we would like to address in our research is how we can, let's say, deploy, let's say, efficient robotic grasping algorithm. Yeah, so the traditional robotic grasping task is defined as in this image. So you have an object, right? Yeah, and usually we use a camera to capture the input for our robot, and then from that object, and you want to localize where the object is, and especially because it's a grasping task, so we want to let's say localize where exactly we can touch the gripper to grasp the object. For example, if I have the mouse on the table like this, then I need to let's say localize the grasping point of my finger. Yeah, and mathematically, then the grasping point can be defined by using just define parameter, and usually we call it the rectangle by definition. So it just simply simplify the problem from the 6D degree freedom pole grasp pole to 4D. So 4D means you have just the let's say the information in 2D and the rotation axis of your objects, which is the theta angle here. Yeah, so this is the traditional grasping task, and when you run any traditional grasping task, and the core idea or the core application could be very simple. So for example, you don't care about the object ID, you don't care about the, let's say what you want to do. For example, let's say you just need to pick up an object and put it into a basket or something like that. Yeah, but with the development of the foundation model like ChatGPT 10, the key thing that we can, let's say, think further beyond the traditional grasping task is we call it something called language-driven grasping. Yeah. So, for example, if you have the image like this, or if I have so many objects on the table, then you can, let's say, clearly tell me which object you want to pick up or which object you want to grasp, right? For example, let's say here you want to grab the green bottle, or you want to grasp the blue bottle, then you can give different command to the robot, and the robot should pick up the right object that you want rather than just pick any random object. Yeah, so we call it the language-driven grasping problem, and actually this can be a problem where we can apply to let's say any robot in our home in the future, because literally if you want the robot to grab an object, and you can give a direct command to the robot, and the robot should grab the object that you want, not any other object. Yeah, so as we do in, let's say, any AI research, then the first question is where's the data that we can solve this problem? Yeah, and the answer is in this paper, and this is the data that we use to, let's say, to solve this problem. Just a quick question for everyone is, if you look at all the images here, yeah, can you tell me that's whether these images are AI generated or are they real images taken by human, or are they mixed images? How many people think that these images are own AI generated? Yes, we have half of the audience. How many think that is kept, taken by human? No. So we have a very high kind of send for data from AI, right? Yeah. The answer is all of the images are AI generated. So actually, it's on the thing here you saw actually is from AI, and there's no real image taken by human at all. Yeah. So the idea is we just have a curious question whether, let's say, if you have a new problem, then of course you need the data, right? If you want to collect the data from the internet, there could be several problems with the privacy, and let's say people don't want you to use the data. If you want to buy the data from company, or let's say private sector, then of course it costs a lot. So we just have a curious question whether we can use AI to generate the data, and whether that data actually becomes useful for our task. Yeah. So let's come to the, let's say, to the first question. What happens if we want to generate kind of new data from AI? Yeah. So this is the principle, or this is the kind of the pathway that we generate the data. So literally we start with some let's say we start by using a big model, for example, like ChatGPT. And then our very first goal is we want to create a lot of prompt. Yeah. So what is the prompt? And simply, for example, you will create this sample. For example, like a ST9, a police fork, and a police ceramic placed on the wooden table. Okay. Yeah. So there's some trick that we can, let's say, manipulate ChatGPT, and ChatGPT can create a lot of different prompt, something like this for us. So how many problems that you can create with ChatGPT 10 actually is a very kind of, it's a very powerful text model. So it can create, let's say in our case, 1 million prompts, which are on, let's say, describe different setup on the table or the thing that you want to create. Okay. Yeah, and then given the prompt like this, then literally we throw that into something called text to image foundation model. In this case, we use stable diffusion. Stable diffusion is just simply a very big model that can generate the image from the text for us. So literally after this step, then you have let's say the image that describe the sentence that you want. Okay, and then the next following 3 steps is we try to label the data as we want as well. For example, here you see that we try to segmentation to segment the nice here, and then segment the part of the nice, and then do the labeling of the grasping pose that we want to have. Yeah. So interestingly, we can create a very big data set with 1 million images, and also can somehow automatically label, let's say, the data set by using a lot of AI model as well. And the whole let's say the whole pipeline can be done within around, let's say, 3 to 6 months without actually collecting any real data or let's say worries about let's say privacy or the problem. Of course, we need to pay some money for ChatGPT to use their API. Yeah, so these are the statistics of our data set, and you can see that in most of the time we have a lot of more sample than existing data set that collected by human or collected by the real robot. For example, if human annotate the data, then normally a big data set can be, let's say, 100,000 images. But if you ask for, let's say, 1 million images, then that's a lot of job for human. And sometimes human we can push the robot to collect the data for us as well. But putting up a lot of robots to collect the data is actually quite goodly set up as well. Yeah, so let's go to the video and see how we go to the experiment. So here we show one interesting experiment. Yeah, so you can imagine that this is the real video that we have we capture from our team. So actually this is the real video. It's not a fake images. Yeah, so we train a method called GR-convert-nest on our data set called graph anything, and also we train that method on the data set as well. Yeah, so in this video, then you can see that the method trained on our data set actually can generate very well to let's say to all the real data as well. And after we run the video, then we kind of try to transform that into the real robot. And you can see that the robot can seamlessly grab an object based on the data that we generated by AI model. Yeah, so one interesting conclusion from this works is if you don't have the data, then actually you can try to find a way to generate the AI, the data with AI, and maybe that data can become useful for the application as well. As in our case, and we have 1 million images. Actually, if we talk about the scale of the data at the moment, then 1 million images is kind of a very large scale data set. And I think in computer vision, then only the ImageNet data set have the same number of images in our, let's say, compared to our data. Yeah, so given this one, then we can see that the robot can grasp the object in both the simple case or in more complicated case or with the, let's say, with the cluster scene. Of course, there's other factor that will contribute to the successful rate of the grasping. For example, let's say the design of the gripper or the trajectory planning of the gripper, but we still have the standard, let's say, component for this problem. Yeah, so after we get the data, then we try to develop something more advanced to let's say to improve the accuracy of our method. And the idea is, given the big data set, and the question is how we can push the state of the art of this problem further. Yeah, so if you still remember the problem, then in many cases, when we talk about language vision grasping, then the object that we want to grasp is actually something that, let's say, not very different from the other object that exists on the table. For example, if I have two mouse here, then my command could be, let's say the robot give me the mouse on the left or something like that. Yeah. So in the view of the robot, and the robot will see two mouse, right? The mouse on the left and the mouse on the right. Yeah. And if I want to ask the robot to pick up the mouse on the left, and that means it need to be distinguished the mouse on the left within the mouse on the right. Yeah. And in vision and in machine learning, we call it the fine-grain problem. The fine-grain problem means you need to classify or you need to distinguish the object within very similar class. For example, let's say instead of doing very general classification problem between dog and cat, let's say category, you need to classify different kind of dog or different kind of cat, which is something much more difficult. Yeah. So in this problem, then we in this paper, then we try to develop a new method on that, and the key idea is we try to construct something called the contrastive load, and the contrastive load we try to push the the feature of the text in one class closer to the object that is described, and pulls let's say, and then try to separate the the other object that is the text does not describe. Yeah, so I think this is more on the mathematical side of the work, so maybe I can skip this part, but maybe you can look at this figure and see what happens if we don't use the contrastive loads and if we use the contrastive load. If you don't use the contrastive loads here, then there's the mix between different clusters, right? So you can imagine that each cluster is like the joint embedding between the text and the image. So if the clusters are mixed together, then that means it's not a good understanding of the model to the data. And the best we can cluster the, let's say, the joint embedding between the text and the vision part, and the higher accuracy you get in the end. Yeah, and then we also perform some, let's say, some robotic experiment as well, as I showed in the previous slide. And with this one, then you can actually grab different objects based on let's say based on the method that we developed. And I hope that one day we can have this kind of system on the real robot that we have in our home. Yeah, there's still actually quite a lot of problem in this domain. For example, the first problem that we have right now is even though we have a very big data set, and then we develop a method that can produce a reasonable accuracy for a problem, the major pain point is very slow. Yeah, like any AI model, and the slow inference is a big problem because literally you need to wait quite a long time to get one inference loop. Yeah, so the main reason that's why our model is quite slow is because most of the time, if you want to obtain a very good accuracy, then that means you need to trade off the inference time. That is usually what the let's say what people in machine learning communities is usually doing now. So, for example, if you want to obtain the best accuracy, for example, let's say in this slide, then the latency can be almost 30 seconds. Okay, yeah. 26 seconds is actually very long in robotics. You can imagine that if you ride a car, then you need to make a decision within less than 1 second. Or if you want to ask the robot to give you the coffee, then literally you want the robot to respond almost immediately, right? Yeah. So it's literally just too long for real-time application with the robot. So we try to develop different methods that can somehow, let's say, maintain the accuracy and also reduce the running time as well. And the technical detail here is we try to make sure that, let's say, instead of using the digital model with 1,000 time step, mean we need to loop 1,000 times to get the final inference result. We try to develop the model that only need to use less time step. For example, let's say 1 time step, 3 time step, or 10 time step. So there could be a trade-off between how accurate your model you want your model to be and how fast your model to be as well. Yeah, I think it's still a very active research field at the moment, and you can see that the accuracy and let's say the trade-off between the latency and accuracy is still a big question for the future research. Yeah. So finally, this is one of our last work last year. So instead of solving the problem in 2D, then we try to solve everything directly in 3D. Yeah, so we do some interpolation to convert the image in 2D, try to generate a depth map, and then try to convert, combine the image in 2D and the depth map, and then try to create a point cloud. We also relabel the ground truth in the 3D point cloud. So, sorry, different from the grasping pole in 2D, where you need just to concerns about the rotation of your graphs of the gripper. In the full 3D environment, and you can approach the object in any angle, and because it provides the full 3D pose of the problem. And we also develop a new method using key concept called negative prompt guidance. So it's just like when you want to grasp the mug, and you want to generate or want to learn where the mug feature is in the point cloud, and then try to generate different text, for example, like the cup, the car, and and then try to map that to different regions of the scene, but not the mugs. The mugs feature should be connected with the mugs text. Yeah, so that's the key concept of our idea. Yeah, so finally, there could be some interesting discussion and experience from the research that we have done. So we showed that the data generated by OM actually is quite useful for let's say for research and maybe for deployment as well. But you should not use let's say continuously use the data generated by OM. There's some work that they already proved that in theory, if you keep putting or keep reusing the data generated by OM, then your model will be crashed very soon. Something like that. Yeah, and in most of our experiments, and we see that the generative model are still very expensive to train and to inference as well. And there could be a huge, let's say, a big need for developing, let's say, a new method to make this model smaller, faster, and less computational expense when we do the inference. Yeah, and finally, there could be a lot of work on generative AI and physical intelligence at the moment, but I believe the future could be very interesting in many tasks. For example, you can see that text to image is kind of done at the moment. You can have very good model that generate very nice image. But there's some bigger problem and more difficult problem, for example, like text to video, especially when you ask the video to have both the image frame and the sound. This is still something very challenging, and text to video is one of the kind of the biggest AI race at the moment, when where all big companies like Google or Facebook, they try to develop something like this. In engineering, then there's other difficult problem that we also try to address some of them. For example, like text to CAD. So CAD is like the 3D design of our of any model that we have, for example, like the table or the computer, and a very different from, let's say, text to image or text to video, when you don't need to care about the physical constraint of the let's say, or care less about physical constraint of the data or the output. And text to CAD is something that you need to really care about the technical constraint of the output. For example, if you have the phone and you want to let's say develop a jack to put it into my let's say into my microphone horn, and somehow you need to fit these two parts together very accurately. Yeah, there are different problems. For example, like text to robot, when you can develop an AI model to help you or to assist the design of the robot or the design of different tasks. And finally, there could be a lot of work, or I believe the future could be on developing different lightweight model that can combine several modalities, for example, like the vision, the text, and the action. And so especially the action that we have, for example, let's say from human data or from robotic data. I think most of the time when we talk about ChatGPT or any big model now, then the key thing that makes this model as so successful is because it have data, right? But the problem is when you look at robotic or when you look at different fields, and for example, like medical field, sometimes, for example, let's say in medical field, we have a lot of data, but we cannot utilize all of these data like the way that people utilize internet data to train ChatGPT. Or if you look at the robotic field, then actually we don't have that big data, let's say, at the internet scale to train a model. So I think that's why that is still a very big question for both the research community and the industry to see whether how to get the right data, the legal data that we can train a model, and then finally combines the modality of these data, for example, like text, vision, or the action, or any more modality that you have, and then train a big or lightweight model to serve the foundation model for the application. Yeah. All right. Thank you. I think that's all.
All right, thank you, Anhe. And are there any questions from the audience?
So thanks for the presentation. It's very interesting. So my question is related to the 2D to 3D, like a G dancer, right? So that model. So when you do the 2D to 3D transfer, like conversion, does your model consider like consider what happening before and after the current frame, or like did you achieve it by one by one each frame, or like is end-to-end solution?
Yeah. So I think in this work, then we literally don't care too much about the temporal domain. We just construct the 3D directly from the depth map of the current image, because I think later on, there could be some penalty line that we can handle the inconsistent in temporal domain later. Yep.
I'm wondering what are the most difficult challenges within physical intelligence, and what makes them the most difficult?
That's a very interesting question. Yeah. So I think right now there could be several challenges, but I think the most difficult challenges is we don't have a good hardware. Yeah. So it's like you can imagine that's we have ChatGPT, right? We have a student who use ChatGPT to complete the exam and maybe get a very good mark, and they can pass several tests as well. We have different big model that can do finance, that can do medical thing. But the basic question is we don't have any robot that can open any cab door. Yeah. So if I ask, let's say I ask everyone to bring the door from the house to here, and I challenge everyone in the world that develop the robot that can open that door, then actually this is still a very difficult problem, and because the robot somehow cannot understand how to push, to pull, or how to open the door, or how to just sit in front of the door and wait the door automatically open by itself. And then I think the hardware and the design of the, let's say, of the robot is still a big question. It's just like the reason that why we have ChatGPT and any other big AI model right now is because we have good GPU. Yeah, and then the GPU actually accelerate the rest of the thing, and you can imagine that the theory for deep learning for convolutional neural network is kind of we have that 40 years ago. But we need to wait around 20 years to get the GPU and then to apply that to the real life. Yeah.
Thank you. All right, thank you, Anna. So I just have a couple of local group reminders. Right, so first of all, I said this at the beginning, but our next event is the Mystery Prediction Contest. So if you would like to take part in this, it's a kind of masked predictors prediction competition. Just a bit of fun. We're going to be putting out the information in 1 or 2 weeks' time, so you could sign up to our local group for that. Finally, yeah, so I mean, this is where you would sign up to the local group to hear about more events like this directly. We have the X site, but also on Facebook. And just a reminder, we have the Royal Statistical Society annual conference in Edinburgh this year. And finally, each year we call for new members to the committee. We're going to be doing so again later in the year. So if you like this sort of events that we put on and would like to be involved and have ideas, then please contact me, contact us, and maybe you could be in the committee next year. So that's all, and thank you very much. It's been a great event, hopefully very interesting talks. Let's thank the speakers again finally.